Hello student, myself Nivesh Prabhakar. Welcome to Antenna and Propagation lecture series. In my previous lecture, I discussed about the different conditions for the 2-point source like current with equal magnitude and opposite phase. Then we discussed about the current with opposite magnitude and with any phase and an element linear array. Now, in this lecture, we discuss about the array of n element with equal spacing and current equal in magnitude and phase for the broadside array. So here we discuss about the broadside array, but here we take the condition is the n element with equal spacing and current equal in magnitude and phase. So now we start the analysis for this. So we can see here the figure. We have taken the element A1, A0, A1, A2, A3 up to the an-1. Consider the n number of identical radiator, that means the elements carry current which are equal in magnitude and in phase. Consider a broadside array with an identical radiator as shown in the figure. So we have here consider this is the broadside array. The electric field at the point P due to an element A0 is given by, we have just write for the A0 equation, E0 I dl sin theta 4 pi omega eta 0 j beta square upon r0 e raised to minus j beta r0 for the E0 field for the A0 component. As the distance of the separation d is very small as compared to the radial distance of the point P from the A0, A1 and A2. That means the distance between these two elements is very small as compared to the distance between the elements and the point P. So we can write the R1 and R0, R2, Rn-1 are approximately same. So we have take the value is the R. So electric field due to the A1 is also given by E1 is equals to I dl sin theta 4 pi omega 0 eta 0 j beta square R1 e raised to minus j beta R1. But R1 is the nothing but the R0 minus d cos phi due to the phase difference. So we can write the instead of this R1 as the R0 minus d cos phi in this equation number 2. Now we solve this equation like I dl sin theta 4 pi omega epsilon 0 is the same, j beta square upon r0 is same. Now we solve this e raised to minus j beta r0 minus d cos phi term. So we have divided this portion into two portions like e raised to minus j beta r0 and e raised to j beta d cos phi. So we can write this equation in the short form as E0 instead of this. We know that this term like I dl sin theta 4 pi omega 0 epsilon 0 j beta square r0 e raised to minus j beta r0 is nothing but the E0 equation. So we have write the E0 and the remaining term e raised to minus e raised to j beta d cos phi. Same as we can write field for the A2 as E2 is equals to I dl sin theta 4 pi omega epsilon 0 j beta square r square e raised to minus j beta r2. So instead of the r2 we can write the r2 is equals to r1 minus d cos phi. So now we put the value of the r2 in this equation. So we can write the r2 instead of the r2 we write the e raised to minus j beta r1 minus d cos phi. So now we solve this equation like in the previous. So we get this term as a I dl sin theta 4 pi omega 0 j beta square r1 and we divided this e raised to portion like e raised to minus j beta r1 into e raised to j beta d cos phi. And this bracket term is nothing but the term of the E1. So we can simply write E2 is equals to E1 e raised to j beta d cos phi. Same, so E2, so and we have the E1 equation. E1 is nothing but the E0 e raised to j beta d cos phi. So we have put the value of the E1 in this equation. So we can write that E2 is equals to E0 e raised to j beta d cos phi, because this e raised to j beta d cos phi and e raised to j beta d cos phi. So we know that this is the summation. So e raised to j beta d cos phi. Similarly, the electric field produced at the point P due to the element a n minus 1 is given by, so we can write for the a n minus 1 term in the generalized form, E n minus 1 is equals to E0 e raised to j n minus 1 beta d cos phi. Total electric field at the point P is given by, we can write the total field is nothing but the summation of the individual field. So this is the E0 plus E1 plus E2 plus up to En minus 1 term. So we can write the equation. Now we put the value for this. Et is equals to E0. E1 is nothing but we have proved that E0 e raised to j beta d cos phi. Same as E2, we have proved that E0 e raised to j beta d cos phi. Up to n term, that means En minus 1 is nothing but the E0 e raised to j n minus 1 beta d cos phi. And now we give this equation as equation number 6. But we know that the psi is equals to beta d cos phi phase angle. So we have just beta d cos phi. Instead of the beta d cos phi, we just write the psi. So equation become Et is equals to E0 e raised to 0 plus E0 e raised to j psi plus E0 e raised to 2j psi plus up to e raised to j n minus 1 psi. Now we have taken the E0 is common from this equation. So this equation becomes the E0 1 plus e raised to j psi plus e raised to 2j psi plus up to e raised to j n minus 1 psi. So now we multiply both the side by the e raised to j psi. So the equation becomes e raised to j psi et in the left hand side, and when we multiply e raised to j psi in the right hand side, so we can write the E0 and instead of 1 e raised to j psi into e raised to j psi is nothing but the e raised to 2j psi. So e raised to 2j psi plus e raised to j3 psi plus e raised to j n psi. Now we subtract the equation number 8 from equation number 7. So we can write that as, so we get finally Et is equals to Et into 1 minus e raised to j psi is equals to E0 e raised to j n psi. So we can rearrange this equation as Et upon E0 is equals to 1 minus e raised to j n psi upon 1 minus e raised to j psi. Now to further analyze, we solve this equation as like Et, we have take the e raised to j n psi by 2 is the common. So in the bracket term, e raised to minus j n psi by 2, e raised to j n psi by 2 upon e raised to j psi by 2, e raised to minus j psi by 2 minus e raised to j psi by 2. So according to trigonometric identity, we can write e raised to minus j theta minus e raised to j theta is equals to minus 2j sine theta. So the resultant field we can write as Et is equals to E0 minus j2 sine n psi by 2 e raised to j n psi by 2 minus j2 psi by 2 e raised to j psi by 2. So now we take this e raised to j term and in this field we can write as e raised to j n minus 1 psi is common, so e raised to j n minus 1 psi by 2. And Et, like the magnitude of this electric field, we can write as Et is equals to E0 sine n psi by 2 upon sine psi by 2. Now, for the broadside array, we first for the measure loop. So in case of the broadside array, the field is maxima in the direction normal to the axis of the array. We know that in the types of array, we learn about the broadside array. Thus, the condition for the maximum field at the point P is given by psi is equals to beta d cos phi is equals to 0. So cos phi is equals to 0. So phi is equals to 90 degree or 270 degree for the major lobe. Thus, phi is equals to 90 degree or 270 degree are called the direction of principal maxima for this broadside array. Same as for the magnitude of the major lobe. Now, the maximum radiation occurs when psi is equals to 0. So, the major lobe, we can write Et by E0 in the magnitude term. Now, for the condition for this is the limit psi tends to 0 when d by d psi sin n psi and d by d psi sin n psi. So, when we solve this, so we get the magnitude for the major lobe is the n. So the n is indicate the number of elements, where the n is the number of elements. Same as for the null. The ratio of total electric field to an individual electric field is given by Et by E0 is equals to sin n psi by 2 upon sin psi by 2. So to find the direction of minima, the equating ratio of magnitude of the field to 0. So we can write as a sin n psi by 2 upon psi by 2 is equals to 0. But the condition for the minimal is the sin psi by 2 is equals to 0. But when the sin psi by 2 is not equals to 0. So the null we can write as sin psi by 2 is equals to 0. So the sin n psi by 2 is equal to sin 0, and we know that the sin 0 is when the m pi, that means the 1, 2, 1 pi, 2 pi, 3 pi. So now we have sin equals to beta d cos pi, and instead of the beta we can write the 2 pi by lambda d cos pi. So now we can write n by 2 pi by lambda d cos pi minima is equals to plus or minus m pi. So we get pi minima is equals to cos inverse plus or minus m lambda upon nd, where here this n is the indicate the number of element in the array, d is the spacing between the elements, and m is the constant value. Now, subsidiary maxima. The direction of subsidiary maxima can be obtained if sin n psi by 2 is equals to plus or minus 1. So sin inverse plus or minus 1 when the value is 3 pi by 2, 5 pi by 2 and 7 pi by 2. And sin n psi by 2 is equals to plus or minus 1 is not considered. Because if the n psi by 2 is equals to pi by 2, then sin n psi by 2 is equals to 1. Which is the direction of principal maxima. So it is not possible for the side loop. So we can skip n psi by 2 in this term. Thus we get psi is equals to 3 pi by n, 5 pi by n, 7 pi by n. So now we have the psi is equals to beta d cos pi, and value of the beta is equals to 2 pi by lambda. So 2 pi by lambda d cos pi is equals to, we have 2 pi by n plus or minus 5 pi by n plus or minus 7 pi by n. So we can write, or we get the phi for the subsidiary maxima is equal to cos inverse plus or minus psi 2m plus 1 upon 2nd. Now beam width of major lobe. Now here we discuss about the beam width of the major lobe. The beam width is defined as the angle between first null. Alternatively, the beam width is the angle equal to twice the angle between the first null and the major lobe maxima direction. Hence, the beam width between the first null is given by Fn BW is equal to 2 into gamma, where the gamma is nothing but a 90 minus 5. So phi minima we have cos inverse plus or minus m lambda upon nd. So phi minima, instead of, we can write this equal to 90 minus phi minima is the gamma. So we can write the 90 minus gamma is equals to phi minima. So we put here, instead of the phi minima, 90 minus gamma is equals to cos inverse plus or minus m lambda upon nd. So now taking cosine of the angle on the both the side. So we take the cosine both the side. So cos 90 minus gamma is nothing but the sine gamma, and cos inverse is the cut. So we get the sine gamma is equals to plus or minus m lambda upon nd. If the gamma is very small, we consider gamma is very small, so sine gamma is equals to gamma, or respectively gamma we can write. So instead of sine gamma, we write the gamma is equals to plus or minus m lambda upon nd. For first null, the m is equals to 1. So we can write the gamma is equals to lambda upon nd. Same as for the second null, we can write the 2 into gamma. So it becomes the first null bandwidth, Fn BW is equals to 2 lambda upon nd. So this is the Fn BW for the broadside array. If the n is very large, then n into d indicate the total length of the array in meter. This is denoted by L. So we can write this Fn BW equation in the length term as 2 pi by lambda upon L in the radian. So now we can also write the 2 upon L by lambda in the radian. Same, converting Fn BW in degree. So this equation is in the radian term. Now we write this equation in the degree term. So Fn BW is equals to 114.6 lambda upon L. So when we solve this, so we can write is 114.6 upon L by lambda in degree. Same as half power bandwidth is nothing but the Fn BW by 2. So we can write this equation as HP BW is equals to 1 upon L by lambda. Or second one in the degree term is, we can write 114.6 divided by 2 is nothing but a 57.3 upon L by lambda in degree. So this is the HP BW half power bandwidth and Fn BW first null bandwidth equation in radian and degree for the n element with equal spacing and current equal in magnitude and phase for the broadside array. Now last one term is the directivity. So the equation for the directivity for this is a d is equals to 2n into d by lambda, or we can also write this directivity in terms of the L upon lambda, that means the d is equal to 2 L by lambda, where the L is indicating the total length of the array and d is the spacing between the element, and n is indicate the number of element in the array. And the lambda, we know that the lambda is nothing but the wavelength. So this is the directivity equation. So in this lecture, we analyze array of the n element with equal spacing and current equal in magnitude and phase for the broadside array. Thank you.